Hello and welcome back to our lecture series on physics informed neural networks. I am Vivek, your host, and today we'll be doing something different. We'll be having a special topic lecture on complex valued neural networks, and I'll be providing an introduction and a high level overview to this topic. So, with that, let's get started. So, let us talk about complex numbers for engineering. So, mathematicians invented these imaginary numbers I. That's what makes the complex numbers complex. And imaginative engineers use them for various applications like Fourier transforms, circuit theory. So your inductances usually has a J in front of it, wave analysis. So complex numbers are like widely used in engineering applications, although they were invented by mathematicians. So they are a very core important element of engineering and physics. And that is good reason to pay more attention to them. So let us discuss this example this is a nice example from signal processing. Let me move my icon here. So Fourier transforms are very widely used in signal processing, and usually what that means is you have a function which is a function of time or it could be a function of space. Here we have said it's a function of time, and it is a signal which is built out of building blocks which are just which have a certain frequency, and they can be represented as complex exponentials. So you can say that your signal is built out of these various building block signals having certain frequencies. And if you want to transform that representation from a signal in time to a signal where you have the frequency information, that's called a Fourier transform. And it involves complex exponentials. So once you do this, you get a representation in terms of its frequencies, but since it's a complex number, it has an amplitude for every frequency and a magnitude. So as you can see there, you have the mod of f of omega and e to the I phi of omega. So typically, if you're from physics or electrical engineering, you would have definitely seen this. And we have a very nice example here. So on the left, we have a picture of this girl, Lena, and this aeroplane. And this is a regular picture. So intensity as a function of space. And then you Fourier transform it. So you change the representation to a frequency domain and you get a complex number. So you have an amplitude and a phase. Then what they do is they take the phase from the Lena image and the magnitude from the aeroplane image and combine that. And you get something which looks like the original Lena image. Then they take the phase from the aeroplane image and the magnitude from the Lena image and combine that, and you get something like the original aeroplane image. And on the right, what you do is you take the phase of the Lena image, throw away the magnitude, set it to 1, and you get something which looks like the Lena image. And the same for the aeroplane. So this shows you that when you're thinking about complex numbers, at least for signal processing, when you do the Fourier transform, the phase is the crucial component. It matters more than the magnitude, and you can basically throw away the magnitude, set it to 1, use a different magnitude. But if you have the phase information intact, that is what will help you reconstruct the original information that you had. So phase is extremely important, and when it comes to Fourier transforms in signal processing, but phase is something fundamental to complex numbers. So in that sense, complex numbers are fundamental to signal processing. So great, we have discussed a nice example from signal processing, which is a well-established field. But what about complex numbers for AI and ML, right? So there is a very famous paper from Yoshua Bengio's collaborators and himself, and this is a quote from the paper which says that whilst complex domain modeling has been widely successful in the signal processing community, example Fourier transforms and wavelets, we have yet to exploit the power of complex valued representations in the deep learning community. Our hope is that this work will be a step forward in this direction. So they hint at the fact that when it comes to AI and ML, complex numbers are still new, and they say that they are using it, but they're hoping that other people are using it. So the question is, are other people using complex numbers in AI and ML applications? Let's find out. So here I've shown you a slide which just is a high level overview of two applications in using complex numbers in AI and ML. So the way they're used is they are they form they they form an idea called complex valued neural networks, which we'll talk about later. But these complex numbers are part of this complex valued neural network framework. And this has been used. There are two examples shown. The one on the right is a MRI fingerprinting practical application for identifying tissue characteristics. And this work was done by at UC Berkeley. And on the left, you have a screenshot of an image from a research paper which came out of Brookhaven National Lab, and they're using complex valued neural networks for image reconstruction application in material science and optics. And if you just look at the figure on the left, you will see that you have a ground truth and they're trying to reconstruct something, and the CNN, which is the complex valued convolutional neural network, outperforms the real valued convolutional neural network, and it's closer to the ground truth. And you probably can't see this, but below they have shown you a chi-squared error histogram, and the error for the complex valued neural networks are lower than the real valued, at least the histogram is towards the left. And they talk about the structural similarity index measure, which is a measure of how similar you are to the ground truth, and that histogram is higher for the complex valued neural networks. So we won't be diving deep into the material science application which was done at Brookhaven Lab, but we'll be diving into the MRI paper. But before that, we need to ask the question, what are complex valued neural networks? So complex valued neural networks are simply neural networks that are built out of complex valued neurons, and the complex valued neurons mirror the conventional neuron, except that the inputs are complex valued, the weights are complex valued, the inputs are multiplied by the weight, summed up, and then they're passed through activation function which supports complex valued inputs and provides a complex valued output, meaning that it can take as input the phase angle, which is a characteristic of the complex number. The latent space for these complex valued neural networks for all sizes, a network ranging from just a single neuron to a deep neural net, a fully complex value, they encode phase and do not split the complex numbers into real and imaginary parts. So first we'll discuss this MRI application, the practical application, and then we'll introduce the famous XOR gate problem and discuss some fundamental implications of complex valued neurons in the context of the XOR problem. So here, as you can see, we have this slide for this practical MRI application. So as we said that a characteristic of complex numbers is the phase, and when you have a complex valued neural network built out of complex valued neurons, its activation function can take in phase as the argument, which you cannot do with real numbers. So on the left, here is the activation function they have used. So you can see that the red and the blue arrows actually represent complex numbers, and on the left you have your inputs. So the red arrows represent complex numbers with a smaller amplitude, and the blue ones are examples with the larger amplitude. And the image adjacent to it on the right shows you what happens after you apply the activation function to these red and blue arrows. And the actual activation function is visualized on the extreme right. So this is the cardioid activation function, which reduces to the reloop on the real axis. So what they do is they take the phase angle, they take the cosine of it, add 1, reduce it by a factor of half, and multiply that by the actual complex number. So it's shown on the bottom right. So what's happening is your complex number z is made out of an amplitude and a phase. So if you apply this, it takes in the entire complex number and it acts on the phase, right? And it is changing the magnitude. So if you write z as mod z e raised to I phi, the half 1 plus cosine of phase of z is going to give you a real number. Amplitude of z is a real number. So that product just means that your amplitude is changing, but the phase remains the same. So as you take sample different complex numbers with varying phase, but keep the amplitude fixed, it'll take as input the phase, change the amplitude based on that phase, and output a new complex number at that phase, but with a changed amplitude. And on the real line, if your x is positive, meaning that your real part is positive, your phase angle is going to be 0, and cosine of that is 1. 1 plus 1 is 2, half of 2 is 1, and you'll get just z, which is the same as x. But if your z if your z is such that your phase is pi, meaning that x is negative, cosine of cosine of phase of z is going to be minus 1. 1 minus 1 is 0, and that's going to be 0. That's the same as max of x comma 0, so it reduces to the ReLU activation. And notice that you're not using ordering like max, which is specific to real numbers. You're actually using a formula which doesn't invoke ordering so that you can use it for complex numbers. And there's also no issues with unbounded functions. So that is what they have visualized here. On the left, as you take complex numbers with a fixed initial amplitude but varying phase, for every phase the amplitude changes, and on the real axis it reduces to ReLU, and the phase remains the same. So as you go from phase 0 to phase pi, the amplitude goes from 1 to 0, and that entire thing is reflected with respect to the real axis. So this is what they have done in their paper, but they've also compared with some other activation functions which act only on the magnitude. So they take as input the magnitude, and the magnitude gets transformed and the phase remains intact. So they have done some systematic comparisons, but their key contribution is actually introducing an activation function that depends on the phase and changes the magnitude, and which reduces to the ReLU on the real axis. So now let's actually discuss some of the results from this paper. So here you see that on the left we have a table of n RMSE, which is just the normalized root mean squared error, and they have used different approaches. So they have used the nearest neighbor approach, which is the conventional approach. They have used a two-channel real and imaginary network, meaning you have a regular real valued neural network and the latent space is real, but you have one real valued one output for the real part, one for the imaginary part. So that's a two-channel real imaginary network, and that they've taken the same network with twice the number of neurons, so it doubles the capacity. And then they have used their special activation function, which acts on the phase such that the magnitude changes but keeps the original phase of the complex number intact. They have used this siglog activation function, which takes as input the magnitude, transforms the magnitude, doesn't do anything to the phase. And then they have used the sigmoid activation function independently on the real and the imaginary part. And T1 and T2 and delta B0 are parameters. So T1 and T2 are tissue parameters, and B0 refers to the magnetic field. So I realized that I haven't introduced the problem. Just a second. So I realized that I hadn't introduced the problem, but we have T1, T2, and B0. So this problem is the MRI fingerprinting problem for tissue characterization. So let's say that, you go somewhere, you need an ID card, you need to open a door, and you usually use your thumb, your fingers, and you have a fingerprint, and your fingerprint is unique to you. The same way, you can have a piece of tissue, and with this MRI application, the tissue interacts with a magnetic field and produces a signal characterized with complex numbers. So it's a complex valued signal, but that signal is signature to that tissue. It's unique to that tissue. It's like a fingerprint, and the tissue is characterized by parameters T1 and T2, and B naught is just the magnetic field from the MRI that interacts with it. So usually you have these parameters T1, T2, and B naught, and you have a signature complex valued signal. And from this signal, you want to reconstruct T1, T2, and B naught to identify the characteristics of the tissue, if it's a cancerous tissue, if it's benign or malignant, that's the term, I think, or to identify white matter, gray matter, things like that. So usually you train a neural network with a lot of data. You have these labels T1, T2, B0. You have the signals, you train it, and then you throw a test test signal at it. So they've used a complex valued neural network and the other real valued ones and compared it. And what you see highlighted in dark is that the NRMSE is lowest for the complex valued neural network with the cardioid activation function for almost all cases. And that means that this specific network, which takes as input phase, and where phase is critical, it outperforms everything else, including the two-channel real valued neural network with one for the real and one for the imaginary output, which means that the good results from the complex valued neural network which use phase cannot simply be explained away by the fact that you have double the model capacity and you have one real channel and one imaginary channel, because it beats that kind of neural network. It is intrinsically complex valued, meaning there's something very special about complex numbers and phase, which is why this neural network is performing so well. So this really brings out the flavor of complex valued neural networks by explicitly using the phase and systematically comparing it with um, different kinds of neural networks where you're systematically changing things. Like you have activation function, which is complex valued, but takes as input the magnitude, one takes as input the phase, then one is the real valued neural network with a real and an imaginary channel. Then you have a pure real valued network, and then you have the conventional approach. So this just systematically builds up complexity and shows you that these complex valued neural networks which use the phase information are really powerful. So now that we have discussed an application, we'll talk about the famous XOR problem and we'll just introduce it. So the XOR problem is a famous problem where it involves nonlinear classification. So you have these 4 points and they have labels. So you have two labels, x1, x2, and here they've been visualized in the R2 plane. So you have labels 1, 1, 1, minus 1, minus 1, 1, and minus 1, minus 1. And two of them belong to class A, the other two belong to class B. So they both belong to different classes, which have been highlighted with the white and the black circles. And there's no straight line which can separate this, meaning that these classes are not linearly separated. And it is well known that a single real valued neuron is unable to separate these two classes. It's a nonlinear problem. But what about complex valued neurons? So the thing is that complex valued neurons can actually solve this XOR gate problem, and they can separate these two classes which have a nonlinear decision boundary. So this table has been taken from this book on complex valued neural networks by Heisenberg. And as we discussed earlier, a complex valued neuron just has complex valued inputs. So real valued inputs are subset of that. So our real valued inputs are fine. They use complex valued weights and they have an activation function which supports complex inputs, will map it to a complex outputs and thereby can process phase. Okay. There is a slight mistake in this table, but let's go through it. We'll find the mistake and just correct it so you know what's going on. So what we're doing here is we are taking our two inputs, x1, x2. which are just the labels 1, 1, 1 minus 1, 1, 1, and 1 minus, minus 1 minus. And you have a weighting vector, which is 0, I, 1. And then you're just evaluating the phase of the output. And your activation function is just you're doing some processing on the phase. So it's, if the phase lies in the first or the third quadrant, you output 1, where 0 and pi are included. And if it lies in the second or the fourth quadrant, with pi by 2 and 3 pi by 2 included, you output minus 1. That is the activation function, and it acts on the phase. Okay. So now if you look at 1, 1 and applying the vector 0, I, 1, you are getting I plus 1, or you can say 1 plus I. So the phase is pi by 4, and the activation function should output 1, and the class is 1. If you apply it on, if you now go to 1 minus 1, you're going to get minus 1 plus I. So the phase is 3 pi by 4, and you should output minus 1, which is fine. That's the correct class. The next is 1. Is this? Next is actually minus 1, comma 1. So you're going to get 1 minus I, which actually is 7 pi by 4, the argument. So that's the mistake they've made. And since it's 7 pi by 4, the class is minus 1, and the output is minus 1, which is fine. And the last one is minus 1 minus I. So your z becomes minus I minus 1. Your argument is 5 pi by 4, which means your activation function outputs 1 and the class should be 1. So that is the mistake. And as you can see, this solves the XOR problem, which is a nonlinear problem. And the question is, why do we care about this? So the goal of AI at a fundamental level is to mimic human or biological intelligence. And deep learning is a subset of AI. Neural networks are a subset of deep learning. And neurons are like the fundamental processing units making up neural networks. And the artificial neuron should mimic the biological neuron. And the biological neuron has been recently shown to compute the XOR gate in this science paper. So they say that in this work, we investigated the dendrites of layer 2 and 3 pyramidal neurons of the human cerebral cortex. In these neurons, we discovered a class of calcium-mediated dendritic action potentials. These dendritic action potentials enable the dendrites of individual human neocortical pyramidal neurons to classify linearly non-separable inputs, a computational conventionally thought to require multi-layered networks. So this was found later. So the complex valued stuff I showed you with the neuron happened in the 1960s, but the biological finding was later and it was published in Science and very recent, 2020. So we clearly see that the complex valued neuron is mimicking the biological neuron, which is something we want at the fundamental level. And that's why we care about this XOR. So taking this one step further, not only does a complex valued neuron solve nonlinear decision boundaries or solve nonlinear classification problems, but even a single layered complex valued neural network can do this. And if you take the real valued counterpart, it struggles. So for example, we can actually go back 2 slides. And here, if you look at what happens to the real valued counterpart, that is the same as saying you would want to take the W1 and W2 as real numbers. If you do, everything is going to collapse to the real axis. So your phase is always going to be 0 or pi, which means this activation function is always going to output 1 and you have a single class. So in this very example, you can see that the real valued neuron has lesser functionality as compared to the complex valued neuron. But going to a one step up, which is the complex valued neural network as opposed to a real valued neural network with a single layer, here what they're trying to do is they have these two nonlinear uh, decision boundaries, a circle and a spiral, meaning that you have these nonlinear shapes and you're trying to find a decision boundary which isn't a straight line, which separates these two shapes shown with the red and the blue dots. And this paper was published in Nature Communications. So they actually designed hardware which supported complex valued arithmetic and which could optically process complex valued signals, meaning the hardware itself was optimized for complex valued neural networks and could also obviously handle real valued neural networks. So they built hardware to do this, and then they showed that this single layer complex valued neural network could solve a nonlinear classification problem, whereas the same neural network with real valued neurons could not. And as you can see here, so the activation function they use is the absolute value, because that is the corresponds to the intensity of light, so that has a physical meaning. But the thing is, if you take a single layer with two inputs x1, x2 and weights, you can actually do the math on pen and paper and show that for a real valued neuron you'll get two lines as a decision boundary, but for a complex valued neuron you actually get a conic section, a quadratic surface, which is why you can actually separate a nonlinear problem. And for the spiral, they had four neurons and it was a slightly larger network. But we can clearly see that the complex valued neural network solves the nonlinear classification problem, whereas the real valued neural network outputs a bunch of straight lines. So it definitely is more functional. And this paper built hardware and then demonstrated it, and it was published in Nature Communications very recently. So this just shows you that complex valued neural networks are highly functional as compared to the real valued counterparts. The other nice thing is the universal approximation theorem was also recently published for complex valued neural networks in 2023. I haven't really gone through the paper, but it exists and that's really great. The other thing is physics informed neural networks is something that I'm interested in, and this lecture series is about that. So the very first example in the main PINN paper was about the Schrodinger equation, which is intrinsically a complex valued problem. You're not just representing physics with complex numbers, but it intrinsically is complex valued. And that, funnily enough, was the first example in this PIN paper. But they're using real valued neural networks. So it makes sense to actually explore a complex valued neural network as the universal function approximator in this PIN problem for the Schrodinger equation example. And we also discussed a real world application where I use pins for motion tracking. So here you have like an aircraft which is moving and you want to track its 3D orientation and the different angles it makes with respect to all the three planes shown here. And you can characterize that using quaternions, which are hyper complex numbers. And you might have data from sensors which provide you with acceleration and angular velocities in a body fixed frame. But the point is that I use a real valued neural network to represent orientation in the form of quaternions, which are hyper complex. So again, it makes sense to maybe think about extending a complex valued neural network to a hyper complex valued neural network and using it for this real world application where you have a pin to estimate orientation. And we did get good results to the proof of concept. So this is the data fitting on the sensor data, and this is the validation with respect to the ground truth data, and the results are pretty good for parts of the signal which are dominated by low frequency characteristics. But when we go to high frequency snippets of the signal, it fails. And there is this paper called Siren, which is again trying to represent complex valued signals and its derivative with real valued neural networks having periodic activation functions. So again, it would actually make sense for even the Siren paper and our motion tracking problem to maybe use a complex valued or a extend that to hypercomplex valued neural network to actually represent our signal and its derivatives. Um, and that actually brings us to the summary and conclusion for this talk. So complex valued neural networks, there are like these four verticals. So when it comes to like the math, it's a natural mathematical extension. Just like we go from real numbers to complex numbers, we're going from real valued neurons to complex valued neurons, and that adds functionality. It's a natural physical representation for wave-based physics, signal processing, and inherently complex valued domains like quantum mechanics. And then biologically, it's a natural abstraction for biological neurons as they can compute the XOR gates, and complex valued neurons have been shown to compute the XOR gate even before that biological paper. And in terms of like the novelty and opportunity, you can take any application you want and just compare complex valued neural networks with your real valued neural networks. So you just solve your problem which you are going to anyways for an application using real valued neural networks, and you just throw in complex valued neural networks by comparing it to the RVNNs. You can connect it to physics informed neural networks. So in physics informed neural networks, are using a universal function approximator to represent the hidden physics. But if you're representing a complex valued or hyper complex valued quantity, you might want to use a complex valued or a hyper complex valued neural network to do that. There's scope to develop complex valued neural networks from scratch in Julia. And why am I saying this? That's because there isn't a lot of support or software for complex valued neural networks, and Julia is a primary scientific computing language. So if there is scope to build something from scratch, it's better to do it in Julia. And if that's done in Julia, that can be packaged, converted into a package, and that's contribution to the Julia open source community, which is again a valuable opportunity and it's novel. And it can be used for a math for machine learning course project where it's a more theory course or even like a computer science course. So these are all the opportunities, and I hope I've given you a flavor of why we should care about complex numbers and complex valued neural networks in context of AI and ML and how they connect to physics and physics informed neural networks and how they have biological and mathematical significance. So I hope you enjoyed this talk. Thank you, and I'll see you next time.